This question is about electrolysis. A student investigates the mass of copper produced during the electrolysis of a copper chloride solution. So let's stop and think about that. So if it is a copper chloride solution, that means that the copper chloride is dissolved in water. So let's think about the ions involved. So we're going to have copper ions, right? And we're going to have chloride ions. But because it's a solution, it's dissolved in water, H2O. And we can break down H2O into being a H plus and an OH minus ion. Okay, so in this copper chloride solution, we have copper ions, chloride ions, H plus ions, and OH minus ions. Figure 12 shows the apparatus. So in figure 12, we can see this DC power supply. So this could be like a battery, which is connected to our two electrodes, right? Inert carbon electrodes, inert meaning unreactive. So we've got a positive one here and a negative one here. And they are in the copper chloride solution, as we've just discussed. Now notice that at this positive electrode, we can see bubbles forming, which implies that there is a gas being produced. And this is confirmed in the question. So this first question asks, which gas is produced at the positive electrode, which we call the anode? So if we're thinking about the positive electrode, well, the positive electrode is going to attract negative ions. So straight away, we can rule out the copper and the hydrogen ions. So we're left to think about maybe chlorine gas or this OH minus. Well, if you think back to the priority rules of what will be formed at each electrode, a halide ion will always take priority at the anode. Therefore, the answer to this question was chlorine gas, for 1 mark. Copper is produced at the negative electrode, the cathode. What does this tell you about the reactivity of copper? So, the negative electrode is going to attract positive ions. So from what we discussed before about the ions present, we're now thinking about the copper ions and the hydrogen ions. Now the rule at the cathode is that the less reactive element will be formed. And we are told that copper is produced. Therefore, this tells us that copper is less reactive than hydrogen. Table 4 shows the students' results. So in Table 4, we can see the time in minutes. Notice that 3 is missing. We've got 1, 2, 4, and 5. And then we've got the total mass of copper produced in milligrams for experiment 1, 2, and 3. And then we calculate a mean. So, this question asks us to determine the mean mass of copper produced after 3 minutes. Now, notice the command word for this question is determine, not calculate. Okay, so that's telling us that in the mark scheme, there is actually a range of possible answers that we're allowed. So let's look at the pattern in the mean. So the mean at 1 minute was 0.6 and the mean at 2 minutes was 1.2. So how do you get from 0.6 to 1.2? Well, you add 0.6. So let's just try and see if that pattern's the same if we include 3 minutes. So if we're saying that at 2 minutes, it's 1.2, right? We could say that at 3 minutes, let's follow that same pattern. So let's add 0.6, and that will give us 1.8 milligrams. Right, that looks about right. Let's see if that works for 4 minutes then. So let's do the same. Let's add the 0.6. And that does give us 2.4. Okay, so 1.8 would be a perfectly reasonable answer. It did say in the mark scheme to allow a range between 1.7 and 1.9 for the 1 mark. Calculate the mass X of copper produced in experiment 2 after 5 minutes. Use table 4. So I've shown table 4 beneath this question, and we are trying to work out this value here, the value of X. So how are we going to do that? Well, we've got a value of experiment 1. We're looking for the value of experiment 2. We have the value of experiment 3, and we have the mean. So let's think about how we would work out the mean. Well, to work out the mean, we add together our different values. So our value from experiment 1, which was 3.02, plus our value from experiment 2, which we're calling X, plus our value from experiment 3, which is 3.01, and then we divide that by the number of numbers. So in this case, we've done 3 experiments, so we divide by 3. And we know that that's going to give us 3.06. Okay, so let's simplify that. Let's make that look easier. So we can times both sides by 3. So that'll get rid of that big divider by 3 on the left-hand side. So that will leave us with 3.02 plus 3.01 equals 3.06 times 3, which is 9.18. Right, and that should be plus X as well on the left-hand side. So now we can simplify this, 3.02 plus 3.01, to give us 6.03 plus X equals 9.18. So therefore, X is 9.18 minus 6.03, which if you type in your calculator, gets you 3.15 milligrams. And that is the correct answer for 2 marks. You would have gained 1 mark for constructing this correct equation using the mean. And then the 2nd mark comes for having the correct answer. The copper chloride solution used in the investigation contained 300 grams per decimeter cubed of solid copper chloride dissolved in 1 decimeter cubed of water. The students used 50 centimeters cubed of copper chloride solution in each experiment. Calculate the mass of solid copper chloride used in each experiment. So to be able to answer this question, we need to be able to convert between centimeters cubed and decimeters cubed. So we need to know that there are 1,000 centimeters cubed in 1 decimeter cubed. And that's going to really help us in this question. So let's think about the information we've been given. We've been told that there are 300 grams per 1 decimeter cubed. Okay? So let's rewrite that differently, this time using centimeters cubed. So we can say 300 grams per 1000 centimeters cubed. Now the students are using 50 centimeters cubed. And we want to know how many grams that is. What's the mass? So to get from 1000 to 50, we divide by 20. So what we've done there to the volume, we now need to do to the mass. So if we do 300 divided by 20, you get 15 grams. So we're saying that there are 15 grams per 50 centimeter cubed. Okay, and that's the correct answer for 3 marks. Now, obviously with this being a calculation question, there were lots of different ways that you could get to the answer. So you could have converted between centimeters cubed and decimeters cubed at different points. Okay, so rather than converting this here, decimeter cubed, into centimeters cubed, you could have converted the 50 centimeters cubed into decimeters cubed. So that would have meant that you did 0.05 times 300, which again would just get you the 15 grams. Or you could have converted the 300 grams into 0.3 and then times that by 50, again giving you 15 grams. Okay, so they're just 2 different ways that you could have done it, but this way that I've shown is perfectly fine for 3 marks. Okay, so you get 2 method marks and 1 mark for a correct final answer. This question is about sodium and chlorine. Figure 13 shows the positions of sodium and chlorine in the periodic table. So what we can see in figure 13 is we've got sodium here, Na, and chlorine here, Cl. The question asks us to state one difference and one similarity in the electronic structure of sodium and chlorine. So, if we look in the periodic table, we can see our groups. So remember, the groups are the vertical columns. Okay, so sodium is in group 1 and chlorine is in group 7. Now, the groups of the periodic table tell you how many electrons are in the outer shell. Okay, so we've said sodium is in group 1, therefore sodium has 1 electron in the outer shell. Chlorine is in group 7, therefore it has 7 electrons in the outer shell. Now, the horizontal rows, okay, that run like this, across the periodic table are called the periods. Okay, and elements in the same period have the same number of shells. Now, hopefully you can see that sodium and chlorine are in the same period. Okay, they're in the same horizontal row. Therefore, they both have the same number of shells. So for my answer, one difference, I would write they have different numbers of electrons in their outer shells. Okay, you could specify how many, as we just did before, in their outer shells. And then for the similarity, I would say they have the same number of electron shells. because they're in the same period. Sodium atoms react with chlorine atoms to produce sodium chloride, NaCl. Describe what happens when a sodium atom reacts with a chlorine atom. Write about electron transfer in your answer. So, sodium is a metal and chlorine is a non-metal. Therefore, in this question, we're talking about ionic bonding, the bond which occurs between a metal and a non-metal when electrons are transferred. So, let's start by talking about what happens with sodium. So, as we've previously discussed, sodium is in group 1, so it has 1 electron in its outer shell. Now, in order to become electronically stable, sodium wants a full outer shell. And the easiest way to do that is to lose that 1 outer shell electron. And this is going to leave us with a positive ion. And the reason for this is that now there are more protons than electrons. Okay, so sodium here has lost 1 electron. And now let's think about chlorine. So as we just discussed, chlorine is in group 7. It wants a full outer shell. Okay, it wants 8 electrons. So it's going to gain an electron, which I'm going to show here in purple, therefore giving it a 1- charge. So we've now formed a negative ion because there is 1 more electron than proton. Okay, so chlorine has gained 1 electron. So now the question is, where has this electron that chlorine has gained come from? Well, this electron from on the chlorine atom has come from the sodium. So when sodium has lost its electron, chlorine has essentially picked it up to give it a full outer shell. So as a final statement, I might say the electron lost from sodium was transferred, because we need to talk about electron transfer, to chlorine. Okay? Now this was a 4-mark question. You get 1 mark for talking about sodium losing 1 electron. So 1 mark for saying sodium's going to lose an electron, and 1 mark for saying that it's going to be 1 electron it's going to lose. Then our 3rd mark comes from talking about chlorine gaining 1 electron. So again, you get 1 mark for talking about the gaining of an electron, and that 4th mark comes from specifying that it's going to be 1 electron that it's going to gain. Okay, so in this bit here we're talking about sodium, and here we're talking about chlorine. Now it is specific in the mark scheme, right, that we need to talk about chlorine, not chloride. Okay, because chloride, remember, is the ion. So chlorine is the element, chloride is the ion. The reaction between sodium and chlorine is an exothermic reaction. Complete the reaction profile for the reaction between sodium and chlorine. So we're told that it is an exothermic reaction. Well, that means that heat energy is released in the reaction. Okay? So let's think about that in terms of our reaction profile diagram. Well, that means that the relative energy of the products is going to be lower than the relative energy of the reactants. Okay, because that energy is being released into the atmosphere. So now all we need to do is join that line for the reactants and the products, and we do that using a curve. Now the curve goes up and down. Forms a sort of hill shape. And if you remember, this change in energy here, we call the activation energy. Okay, and that's the minimum energy required for the reaction to take place. Okay, so it was a 2-mark question. So you needed to think about the energy of the products being lower than the energy of the reactants, and then getting that curve that goes up and then back down for 2 marks. A student plans a method to prepare pure crystals of copper sulfate. The student's method is to add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker, and when the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. The method contains several errors and does not produce copper sulfate crystals. Explain the improvements the student should make to the method so that pure crystals of copper sulfate are produced. So let's start by thinking about the chemicals involved. Now the student is using hydrochloric acid, but is wanting to make copper sulfate crystals. Well, really, the student should have used sulfuric acid instead of hydrochloric acid, because we need a source of sulfate ions. And because sulfuric acid is H2SO4, and an SO4 2- ion is a sulfate ion, we need the sulfuric acid to produce a sulfate rather than a chloride, which is what would be formed with hydrochloric acid. Now, the student is also using calcium carbonate solid, but wants to make copper sulfate crystals. So the student should have used copper carbonate instead of calcium carbonate. Looking back now at that same step on the method, the student said to add 1 spatula of calcium carbonate. Well, really, the student should have added that carbonate in excess to ensure that all of the acid fully reacts. Now, if we have added an excess of solid, that excess of carbonate, we now need to use a process to remove that excess solid. And this process is filtration. So the next improvement we could suggest is to filter, to remove the excess carbonate. And now to make crystals, the last improvement could be to heat gently and leave to crystallize. So this question built upon our practical skills. It was a slightly more demanding question than simply recalling a method, because we had to suggest and explain improvements to a student's method. So this was a slightly harder question. Now, as I said, it was worth 6 marks, and the marking for this question had a levelled approach. So some things the examiners were looking for was for you to identify relevant points. They wanted you to give your relevant points in detail, which is why it's an explain command word as opposed to state or describe. They were looking for your points to be logically linked, and they wanted you to give a clear account. This question is about the halogens. Write the state symbol for chlorine at room temperature. So, we are told that chlorine is Cl2. So it's two chlorine atoms bonded together. Now, when we have two nonmetals bonded together, that is a covalent bond. So we can say that Cl2 is going to be a simple molecular substance. And one of the properties of simple molecular substances is that they have low boiling points. Okay, and this is due to the weak intermolecular forces. So, we can say that chlorine is going to be a gas at room temperature because of its low boiling point. And the state symbol for a gas is G. Figure 4 represents one molecule of fluorine. Complete the dot and cross diagram on figure 4. So, fluorine is one of the halogens, which means it's diatomic. So, just like we said chlorine was Cl2, fluorine is F2. So, let's look at what's happening on figure 4. So, for this fluorine atom, we're representing electrons as crosses. And for this fluorine atom, we're representing electrons as dots. Now, we need to represent the covalent bond which is occurring between these fluorine atoms. And remember that a covalent bond is the sharing of electrons. So this fluorine's going to share an electron. This fluorine's going to share an electron. In the aim to give each of these fluorine atoms a full outer shell, i.e. allowing them to have 8 electrons in their outer shell each. So, let's start by sharing the first fluorine's electron, which we're showing as a cross, and then the second fluorine is going to share an electron, which we will show as a dot. So now we need to make it that on this circle there is 8 electrons, and on this circle there is 8 electrons. Okay, so currently on this fluorine circle we've got 1, 2, 3. Okay, so we need to add in 5 more crosses, and on this fluorine's shell again we have 3, so we need to add in 5 more dots to give us the full outer shell. A fluorine atom can be represented as F919. We'll talk about that in a minute. What is the total number of electrons in a fluorine molecule? Okay, F2. So notice the difference between a fluorine atom, right, which is just the singular atom, in comparison to a fluorine molecule, okay, because that's 2 fluorines bonded together. So, let's have a little look at this. So, what does this tell us? Well, this smaller number, okay, the 9, is our atomic number. Okay, and our atomic number tells us the number of protons. The bigger number, the one on top, is the mass number. Okay, and the mass number tells us the number of protons added to the number of neutrons. Okay, now hopefully we understand that an atom is neutral. Okay, it has an overall neutral charge. And this is because in an atom, the number of protons is the same as the number of electrons. So, the atomic number is 9, so that means that in one fluorine atom, there is 9 electrons. Now we want to know how many electrons are in a fluorine molecule, which has 2 fluorine atoms. So we need to do 9 times 2, which gets you 18. Okay, so the correct answer to this question was 18. Now a lot of people would have ticked 14 because they would have simply counted the number of electrons that we put in the diagram in the previous question. But remember that that diagram only showed outer shell electrons. Aluminium reacts with bromine to produce aluminium bromide. Complete the balanced chemical equation for this reaction. So, we've got aluminium plus bromine, which remember is Br2 because it's diatomic, and this makes 2 moles of aluminium bromide. So the first thing we need to do is figure out what is the formula for aluminium bromide. So aluminium bromide is going to be an ionic substance, okay, because aluminium is a metal and bromine is a non-metal. So aluminium can be found in group 3 of the periodic table, which means that it makes 3 plus ions. Bromine can be found in group 7 of the periodic table, which means that it makes 1 minus ions. Now, to figure out what sort of ionic compound it makes, we can do this little trick where we swap and drop the numbers. So we take this 3 down to the bromine, okay, and we take this 1 down to the aluminium. And this gets us AlBr3, okay, because we don't need to show that 1 next to the aluminium. Another way you could think about it, if you don't like doing the swap and drop, is to think, if I've got an aluminium 3 plus ions, how many 1 minus ions do I need to counteract that charge to make it neutral? Okay, so you're going to need 3 minuses to counteract that 3 plus ion. So either way you do it, you get aluminium bromide to be AlBr3. Okay, now what we need to do is we need to balance this equation. So let's start by thinking about the aluminiums. So currently on the left-hand side, we have 1 aluminium, but on the right-hand side, we have 2 aluminiums. So we need to put a 2 in front of that Al. Okay, now let's think about the bromines. So at the moment, we have 2 bromines on the left-hand side, and we have 6 bromines on the right-hand side. Okay, because we've got 2 lots of Br3, which gets you Br6. So how do you get from 2 to 6? Well, we need to times it by 3 on this side. Okay, so the final answer was 2Al plus 3Br2 makes 2AlBr. Okay, this was a 2-mark question. You got 1 mark for recognising that aluminium bromide is AlBr3, and the 2nd mark comes from balancing that equation correctly. When chlorine reacts with potassium bromide, chlorine displaces bromine. And this is shown in the equation. So we've got chlorine, Cl2, reacts with potassium bromide, KBr, and that's going to make bromine, Br2, and KCl. So notice how the chlorine has taken the place of the bromine in the compound. This question asks, explain why chlorine is more reactive than bromine. So it's an explain question. So we've got to dig deep into our understanding of electronic configuration to explain why chlorine is more reactive than bromine. So what I've done here is I've drawn the electronic configuration of chlorine, which has 17 electrons, and bromine, which has 35 electrons. So hopefully you can see that chlorine is a smaller atom. And that's actually worth your first mark. So I'm going to write that chlorine is a smaller atom. Okay. I could have also written something along the lines of, it has fewer shells. Okay, or energy levels. Now, what does that mean? Well, that means that chlorine has less shielding than bromine. Okay, because there's less shells between these outer electrons to the nucleus in chlorine than there is between the outer electrons in the nucleus in bromine. Another way you could have phrased that for the second mark was to say that in chlorine there's a greater attraction between the nucleus and the outer shell. Okay, so a greater attraction between the nucleus, which has a positive charge, and the outer shell electrons, which have a negative charge. And now the final mark was to link that into being more reactive. And whenever we're talking about reactivity, we're talking about how easy it is to gain or to lose electrons. So what we can say is chlorine is more reactive because it is easier for chlorine to gain an electron than bromine. Okay, remember, because both of these are in group 7, they want a full outer shell, so the easiest way from getting to 7 to 8 is to gain an electron, okay, rather than losing 7 electrons. So it was a 3-mark question, 1 mark for saying that chlorine is a smaller atom, or it has fewer energy levels, or the outer shell is closer to the nucleus. The 2nd mark for saying that chlorine has less shielding, or saying that there's a greater attraction between the nucleus and the outer shell. And then the final mark, linking it into reactivity. Therefore, it is easier for chlorine to gain an electron, okay, because the electron is going to be more attracted to the chlorine nucleus because it's closer, yes, as opposed to the bromine nucleus because of these shielding, the shielding due to the inner shells. This question is about structure and bonding. Figure 5 shows parts of the structure and bonding in diamond. Explain why diamond has a high melting point. So let's think about what we know about diamond. So diamond is made up of lots of carbon atoms bonded to lots of other carbon atoms. And when we have a carbon bonded to another carbon, that is a covalent bond. Okay, because it's a bond between 2 nonmetals. So we can say that diamond has lots of strong covalent bonds. Now, let's think about what type of structure diamond is, because we've spoken about the bonding. Now let's talk about the structure. So diamond is something called a giant structure, okay, or a giant covalent structure. Basically meaning there are lots and lots of atoms, okay, and there's lots and lots of bonds between those carbon atoms. So it's a giant covalent structure as opposed to a simple covalent structure, which might be something like Cl2. Okay, so we've spoken about the structure, we've spoken about the bonding. Now we need to tie our answer back to explaining why that means diamond has a high melting point. So we can now say as our final mark that we're going to need lots of energy to break, okay, or to overcome those strong bonds. Yes, those strong forces. So this was a 3-mark question. You got 1 mark for talking about a covalent bond. You got 1 mark for identifying that it's a giant structure. And in fact, if you said giant covalent structure, that's 2 marks. And then the final mark was for talking about lots of energy is going to be needed to break or overcome those forces. Figure 6 shows part of the structure and bonding in sodium chloride, NaCl. So in figure 6, we can see a chloride ion and a sodium ion. Explain the conditions needed for sodium chloride to conduct electricity. So, first of all, let's think about sodium chloride. Now, the fact that figure 6 has told us that it's made of chloride and sodium ions tells us that sodium chloride is made of lots of ionic bonds. So it's got ionic bonding. And in fact, it is a giant ionic lattice. So, now let's think about this word electricity. And this is where a bit of knowledge from GCSE physics is going to come in. So, electricity is caused by a current, okay? And a current is a flow of charge. Okay, so when you've got a movement of charged particles, you have a current. So let's just write that here. Let's write a flow of charge. Now, hopefully we agree that ions are charged particles, okay, because they are atoms which have either gained or lost electrons. But at the moment, in our giant ionic lattice, those ions can't really move. They can vibrate about a fixed position, but they're not free to move around and carry charge. So the conditions needed to let those ions move is we either need it molten, okay, or liquid, or dissolved. Okay, so we could say dissolved, for example, in water, or another way of putting that would be to say aqueous. So the conditions are either molten or dissolved, but now we need to explain that condition. So that would mean that the ions are mobile. Okay, so they are moving around the structure and they are carrying charge. Okay, so this was a 3-mark question. 1 mark for the first condition, which is molten or liquid. The 2nd mark for the second condition, dissolved or aqueous. And then the final mark was for talking about the ions being mobile or free moving. So the idea they can move around the structure and carry charge. Figure 7 shows the structure of sodium. Describe how sodium conducts thermal energy. So, sodium is a metal, so it contains metallic bonding. And that metallic bonding is what we can see in figure 7. So we can see rows of positive ions. So here these are our Na plus ions. And surrounding those positive metal ions is a sea of delocalized electrons. Okay, and this is the reason why sodium can conduct thermal energy. So the first point I'm going to make in my answer is that in metallic bonding, there are delocalized electrons. Okay, and these come from the outer shells of the atoms. Okay, when we go from atom to positive metal ion, yes, we lose an electron. Okay, so that's my first point. We've got delocalized electrons. And because these electrons are delocalized, they are free to move around the structure. Okay, and what does this mean? Well, if those electrons are free to move around the structure, they are free to transfer energy. Okay, so free to transfer energy through the structure. Okay, so this was a 3-mark question. You got 1 mark for pointing out that we have delocalized electrons. 1 mark for stating that those delocalized electrons are going to be free to move around the structure. And then the final mark is talking about the electrons being free to transfer energy through the structure. Group 2 metal carbonates thermally decompose to produce a metal oxide and a gas. Give the formula of each product when calcium carbonate, which is CaCO3, is heated. So we know that when it's heated, we're going to produce a metal oxide and a gas. So let's start by identifying the metal oxide. So here, the metal is going to be calcium, okay? And calcium is going to form a 2+ ion. And it's going to be calcium oxide. And an oxide ion is 2-. So using our swap and drop method, we can say that our metal oxide is going to be calcium oxide. Now, thinking about which atoms are left over, we've used up this calcium atom, we've used up one of the oxygens, so we are left with CO2, okay, which is carbon dioxide gas. The relative formula mass of a group 2 metal carbonate is 197. We are given the relative atomic masses of carbon, which is 12, and oxygen, which is 16. We need to calculate the relative atomic mass of the group 2 metal in the metal carbonate. And then we need to name the group 2 metal. So, let's start by thinking about what the formula of this group 2 metal carbonate will be. So let's call the group 2 element X. Okay? And because it's in group 2, it's going to form 2+ ions. Okay? And it's a group 2 metal carbonate. And remember, the carbonate ion has a 2- charge. Okay, so those charges will cancel out to give us the formula of the group 2 metal carbonate to be XCO3. And we are told that that has an MR of 197. So, Now, let's plug in these relative atomic masses of carbon and oxygen. So we can say that X plus the relative atomic mass of carbon, which is 12, plus 3 lots of the relative atomic mass of oxygen, which is 16, gives us 197. Now, if you use your calculator to figure out what 12 plus 3 lots of 16 is, you should find that to be 60. So X plus 60 equals 197. Therefore, X is 197 take away 60. So X is 137. So that is the relative atomic mass of the group 2 metal. Now, we need to figure out what metal that is. So using your periodic table, you're looking for an element in group 2 which has a mass number of 137. And hopefully you can see that that is barium. Figure 8 shows the volume of gas produced when a different group 2 carbonate, W, is heated. So on figure 8, we can see the volume of gas in centimeters cubed on the y-axis. And on the x-axis, we've got the mass of group 2 carbonate heated, which is measured in grams. We want to calculate the gradient of the line in figure 8 and then give the unit. So, firstly, to work out the gradient, we need to do rise over run, which is the change in y divided by the change in x. Now, I have marked on the graph in purple a triangle. Now, you could pick any triangle you want as long as it touches this line. But the bigger the triangle, the more accurate your gradient's going to be. So I've picked this triangle here. So this is my change in y, the vertical change, and this is my change in x, the horizontal change. So, to calculate the change in y, it's going to be the top, which is 330, take away the bottom, which is 50. And that is divided by the change in x. So that's 2 take away 0.3. And typing that in your calculator will give you an answer that's somewhere around 165. Now, because this question involves reading off a graph, there is quite a lot of room for error. So in the mark scheme, it says that any answer between 160 to 174 is allowed. Okay, so 165 fits perfectly within that range. Now we need to give the unit. So what we've worked out here is the change in y, which is measured in centimeters cubed, divided by the change in x, which is measured in grams. So for your unit, all you have to put is centimeters cubed per gram. 24 decimeters cubed of gas is produced when 1 mole of a group 2 carbonate is heated. Determine the relative formula mass of the group 2 carbonate. Use figure 8. So for this question, we need to use the graph from the previous question. Now, there is no value of 24 decimeters cubed that we could read off the graph. However, we could read 240 centimeters cubed off the graph. And we could work out what mass that would be. Okay? Now, if you read that off the graph, you will find that 240 centimeters cubed equals 1.45 grams. Okay. We want 24 decimeters cubed. So let's now convert that into centimeters cubed. So 24 decimeters cubed. And when we convert into centimeters cubed, that's going to give us 24,000 centimeters cubed. So now we know what 240 centimeters cubed is as a mass. We now want to find 24,000. So what we've done there is we've timesed that value by 100. So we now want to times this value by 100. And that is going to give us 145. Now notice in the question it says 1 mole of a group 2 carbonate. Okay, so that means that our answer for the relative formula mass is just 145. A scientist does 2 tests on 4 white solids. The solids are labelled A, B, C and D. So, test 1 is add the sample of solid to distilled water and stir. And test 2 is to measure the pH of the solution after test 1. Table 2 shows the results. So here we've got solid A, B, C and D. We have appearance after stirring and pH. So we have colourless solution and colourless liquid for D. But note that for solid A and B, no solid remained after stirring. But for B and C, there was some solid which remained. So that's going to be important when we come to answer this question. Notice as well the pH values. So solid A has a pH of 14, which is an alkaline pH. Okay, so we're thinking that solid A is going to be a base. Solid B has a pH of 3, which is an acidic pH. So we're thinking that solid B will behave like an acid. Solid C is 9, okay, which is slightly above the neutral pH, which is 7. Okay, so that pH of 7 will be the same as the pH of the distilled water, because water has a neutral pH of 7. We are now told that the 4 solids are magnesium oxide, phosphorus oxide, silicon dioxide and sodium oxide. And table 3 shows the solubility of these 4 solids in water. So solubility is how easily something dissolves. So the information we are given is the solubility in grams per 100 centimeter cubed of water. So how much of these solids will dissolve in 100 centimeters cubed of water? So for magnesium oxide, that is 0.01. So it's very insoluble. Not much of it dissolves. For phosphorus oxide, it's 52 grams per 100 centimeter cubed. Silicon dioxide has a value of 0. So silicon dioxide is completely insoluble in water, and sodium oxide is the most soluble with a value of 109. Identify the solids A, B, C and D. Explain your answers. So what I've written here in the purple is I've just copied out the information from table 2 and table 3. So let's start by thinking about D. So we're told that for D, the solid remains, and it's a pH of 7. Now that means that nothing has dissolved since we added the distilled water. And also notice that silicon dioxide has a solubility of 0. Therefore we can say that D is silicon dioxide. And this is because the pH is unchanged from that of distilled water. Therefore, no solid has dissolved. And this makes sense because we know that silicon dioxide is completely insoluble. Okay, so because it's gone from a pH of 7 in distilled water to a pH of 7 when we've added the solid, we know that nothing has dissolved. So now let's think about C. So for solid C, we're told that some solid remains and the pH is 9. So some of it has dissolved to cause an increase in pH. So C is going to be magnesium oxide. Now from the table we were told that magnesium oxide has a solubility of 0.01. So it is slightly insoluble. So in our answer we would write something like C is magnesium oxide. This is because it is slightly insoluble, yet some of it dissolved in water, hence the pH increase from neutral, so a pH of 7 in distilled water, to a pH of 9. So now we need to decide between A and B, the two which are soluble. And the difference is in the pH. So for A, it's a pH of 14, and for B, it's a pH of 3. Now, sodium oxide is a base, and phosphorus oxide is an acid. And we said earlier that a pH of 14 will be an alkaline, and a pH of 3 is going to be an acid. So using that understanding, we can say A is sodium oxide, because it is a base. So it has a high pH, and it is very soluble. And using the same sort of understanding, we can say B is phosphorus oxide. And this is because it is acidic. Okay, it's quite a strong acid. It's got a pH of 3. And it is soluble. Okay, it had a solubility of 52. So this is how we would set out our answer for this question. We've clearly identified each of the solids, and then we've given an explanation of why we think it's that. And this question was a longer writing style question worth 6 marks. And it had a level base marking criteria. And in order to achieve the top marks, which was 5 or 6, the examiners were looking for you to give relevant points. They were looking for you to give those points in detail. They were looking for the points to be logically linked, and they were looking for a clear account. 10 centimetres cubed of solution B is added to a beaker. Distilled water is added to the beaker until the final volume is 1000 centimetres cubed. The pH of the solution is measured before and after the distilled water is added. Table 4 shows the results. So here we have the volume of solution in beaker, starting at 10, finishing at 1000 centimetres cubed. And then we have the pH of solution B. So at 10 centimetres cubed, the pH is 3. And we want to work out this value of X. So what is the pH of solution B when the volume is 1,000 centimeters cubed? Now, the first thing we need to think about is how have we gone from a volume of 10 centimeters cubed to a volume of 1,000 centimeters cubed? Well, essentially, if we do 10 times 100, we get 1,000. Okay, so the first thing to think about is that we have diluted by a factor of 100. Okay, now we need to recall that when we dilute a solution by a factor of 10, we will see a pH change of 1. Now, 100 is 10 times 10. Okay, so essentially we've diluted it by a factor of 10 once, and then diluted it by a factor of 10 again. So essentially, we start off with a pH of 3. We dilute by a factor of 10, so we're going to add 1. So that's going to give us for 100 centimeters cubed. But then we're going to dilute it again by a factor of 10 to give us 1,000 centimeters cubed, which is going to be 3, add 1, which is 5. And that is the correct answer for 2 marks. This question is about iron. Iron reacts with dilute hydrochloric acid to produce iron chloride solution and one other product. Name the other product. So let's write an equation for what's happening in this reaction. So we have iron, which has the symbol Fe, is reacting with hydrochloric acid, HCl, to produce iron chloride, which has the formula FeCl2, plus another product. And we need to figure out what that other product is. So, first of all, let's try and balance the parts of the equation that we've got now. So we've got one iron atom. Here we have one chlorine atom, but here we have 2 chlorines. So we need to put a 2 in front of this HCl. Now, thinking about the atoms that we have used up. We've used up this iron here. We've used up these 2 Cls here. So what are we left with? Well, we're left with 2 H's. So this other product is going to be H2, or hydrogen. Now the next part of the question says, suggest how any unreacted iron can be separated from the mixture. So iron is going to be a solid. And how can we remove a solid from the mixture? Well, we could use filtration. Also, given that iron is magnetic, you could have also put to use a magnet. And this is one of the alternate answers on the mark scheme. Magnesium reacts with iron chloride solution. 3Mg plus 2 FeCl3 makes 2Fe plus 3 MgCl2. 0.12 grams of magnesium reacts with an excess of iron chloride solution. And we're told that the relative atomic masses of magnesium is 24 and iron is 56. For 5 marks, calculate the mass of iron produced in milligrams. So, let's start by using the information that we've been given. So we've been told that 0.12 grams of magnesium reacts with an excess of iron chloride solution. So I'm just going to write that underneath the magnesium, because I've just rewritten the equation here for convenience. So magnesium, I know I've got 0.12 grams of. Now I can find the moles of magnesium using moles equals mass over mR. The mass we know is 0.12, and the mR, we can use the relative atomic mass of 24. Now typing that in your calculator will give you a value of 0.005 moles. Okay, so that is the moles of magnesium. Now we are concerned with iron, this one. So now we need to compare the molar ratios. So 3 moles magnesium goes to 2 moles of iron. So we now need to convert that molar ratio to work out the moles of iron. So the moles of iron is going to be 2/3 of the moles of magnesium, which is 2/3 times 0.005. And again, putting that in your calculator will give you 0.0033 recurring moles. So that's the moles of iron. Now, for this question, we want to calculate the mass of iron. So we need to use this equation, moles is mass over mR, but rearrange to say that the mass is the moles times the mR. So the moles is 0.0033 times the mR for iron, which is 56. And that gets you a value of 0.1866 grams. Now, getting that far in the question will get you 4 marks. But we need to remember that the question wants us to give our answer in milligrams. So how do we convert from grams to milligrams? Well, we times by 1,000. So 0.1866 times by 1,000 will get us approximately 187 milligrams. Now this question was quite hard. It was worth 5 marks. And the marks in this question were divided up as follows. You would get 1 mark for calculating the moles of magnesium to be 0.005. You'd get the second mark for applying the molar ratio and working out the moles of iron to be 0.0033. The third mark comes from doing this calculation. So rearranging to say that mass is moles times mR and doing 0.0033 times 56. The fourth mark comes from seeing an answer in grams. And then the final mark is for the conversion to milligrams. Explain which species is reduced in the reaction between magnesium and iron chloride. Your answer should include the half equation for the reduction. So let's have a look at the equation. We've got 3Mg plus 2FeCl3 makes 2Fe plus 3MgCl2. So let's assign some charges. So here magnesium is going to have a charge of 0, as is this iron, because they are elements. However, these here, FeCl3 and MgCl2, are ionic compounds, which are made of positive and negative ions, and ions have charge. So, first of all, let's determine the charge of the Cls. Now, Cl is in group 7, so it will have a -1 charge in both. Magnesium here, magnesium is in group 2, so it'll have a 2+ or a +2 charge. And that makes sense because the overall compound has to have a net charge of 0. So +2 -2, okay, because there's 2 -1s, gets us 0. Now, iron is a bit of a tricky one because iron is a transition metal. So it can take different charges. So here we need to sort of work backwards and say, well, if the overall compound has neutral charge and we have 3 1- charges, then iron has got to have a +3 charge, okay, to counteract those 3 minus charges. Okay, now we've assigned our charges. Now we need to think about oil rig. Now, different people have different ways of remembering this. I use oil rig. An oil rig says that oxidation is the loss of electrons, and reduction is the gain of electrons. So let's think about, first of all, which species has lost electrons? Well, that's going to be magnesium. It's gone from 0 to +2. So as a bit of an aside, we can write magnesium has been oxidized. This isn't part of the answer, by the way. This is just some extra information. Now notice that Cl doesn't change. So we could write that Cl- is a spectator ion. Okay, now what the question's asking for, what has been reduced, so what has gained electrons, well, that's going to be the iron 3+. So in our answer, we would write iron 3+ has been reduced. And notice the command word for this question is explain. So here we've stated iron 3+ is reduced. Now we need to explain why that is by saying it has gained electrons. Okay. Now we need to look back to the question. Because in the question it says we need to include the half equation for the reduction. So the reduction is going from iron 3+ to iron. So the ion to the element. So here we need to add electrons to counteract that 3+ charge, and we're going to need 3 of them on the left hand side. Okay, so this was a 3-mark question. 1 mark for identifying it was iron 3+ that's been reduced, and then 1 mark for your explanation, talking about it gaining electrons. And the final mark was for a correct half equation for the reduction.